So, we're the Venturi Flow Testing Group. We're just here to talk to you a little bit today about our test this semester and just the results that we've accumulated from it overall. So, a little bit of background, we were actually tasked with measuring the pressure differential across a restrictor for a Venturi intake system. As of now, optimized Venturi systems continue to advance for broader racing applications. This includes other automotive practices that use these systems, so virtually any combustion engine system. For this test, this was conducted, for the Formula SAE speed team. So a restrictor was actually designed for that purpose, and it was prior to this, it was actually simulated in ANSYS, and our goal was to verify those simulations here, primarily by measuring the pressure differential, and from there we can use that to compute the mass flow rate. And so, if this were to be proven successful, a mass flow rate of 0.074 kilograms per second would be optimal for that. And so that is the key question overall: is can we achieve that mass flow rate? And so we had to factor in a few key assumptions, and that included, uh, assuming that this pre-designed restrictor was a ideal model of what it is. Even though it is 3D printed, assume that the flow is fully developed, which was something that kind of came back to get us when we were actually testing. And of course, that this is an ideal fluid, which nothing usually is. So those were just a few things we wanted to assume. And that's just a little bit about the background for this entire experiment. So, the goal of this experiment overall, as I said before, is to measure the pressure differential across the restrictor. Over here on the right, you can see a picture of our test setup. We have a jig which is connected to the table and connected to our restrictor. We assumed perfect atmospheric conditions during testing, and that the 3D printed restrictor is an exact replica, an ideal model used in these airflow simulations. In order to measure the actual pressure differential, some holes were drilled, and we installed pressure taps at the inlet. One at the throat and one at the outlet of the restrictor, just in order to get a nice flow of data across each of these key points. In order to more accurately achieve these results, we actually varied the voltage to the blower motor to change the flow, instead of doing that manually. And we were able to do that quite smoothly. So again, over here on the right is the picture of the setup and everything that we had so far.
The goal of this experiment was to measure the pressure across a restrictor. We used some assumptions, such as we were testing in perfect atmospheric conditions, and that the 3D printed model, is a perfect replica of the model that was used in the airflow simulations. For measuring the pressure, we installed three pressure taps, at the inlet, the throat, and the outlet of the restrictor. We varied the voltage going to the blower motor to change the flow that was going through the restrictor. For your procedure, your first step is to obtain all needed materials such as the blower motor, restrictor, pressure taps, etc. Drill holes for the pressure taps. We did 3 holes, like I said, at the inlet, throat, and outlet, but someone who is recreating this experiment can do as many pressure taps as they would like. Attach the restrictor to the flow bench. In our case, we needed an adapter, so we 3D printed an adapter that would screw into the table and attach to the restrictor. Connect the pressure taps to the manometer and make sure they are all zeroed and calibrated. Determine the voltage needed to go to the blower motor to be able to change the change the pressure going across the restrictor. For us, we started at about 1.3 volts was when the um, pressure in the manometer started to change throughout the restrictor. Conduct an upscale and downscale test of this experiment. In our case, we varied the voltage by zero point 0.1 volts and recorded the pressure at the three different tap locations every time. And we did that, like I said, for an upscale and for a downscale. And analyze your results once the experiment is over. For equipment and materials, we needed a blower motor that connected to a flow bench, a 3D printed Venturi restrictor. Ours was 3D printed, but it does not have to be for someone recreating this experiment. Pressure taps. In our case, like I said, we needed a 3D printed flow bench adapter and a multi-channel manometer with connection tubes. For this experiment, we only needed to purchase the pressure taps, which were only about $5. Everything else was either supplied to us or we already had. And the number of channels needed for the manometer depends on how many pressure taps you use. We used a 20 channel manometer, but we only used 3 of the channels for the 3 pressure taps, but it really depends on how many taps you are using for the experiment.
So now that we have gone through the introduction, the background, and our procedure and equipment, we can get on to the results. So just right here, we can get the raw data that we gathered from our experiment. So of course, we have an upscale and a downscale, as we discussed earlier, and things to note for the upscale. The inlet pressure of the restrictor actually drops quite a significant amount, which is to be expected. The outlet pressure does not change very much at all. However, the most important part of this is, of course, the throat pressure, which is the minimum diameter that the restrictor actually has to go through. So this pressure actually increases quite a bit, and this was, of course, to be expected. I would like to point out on our downscale test, you can see a bit of a hump going on in our throat pressure data. This can be attributed to just basic equipment error. The readings in the manometer were not 100% accurate. Our hysteresis error showed a bit of a difference going on, but moving on to the most important part, our analysis. So our analysis required us to calculate the pressure differential across the inlet area of the restrictor and the outlet area of the restrictor, and then plot that against the mass flow rate going through the actual throat area of the restrictor itself. So you can see there's kind of a bit of a logarithmic fit to this line as given in our background information. However, it doesn't quite fit as well as we would hope. But additionally, the mass flow rate actually only scales from about 0.02 kilograms per second to about 0.025, which of course is nowhere near the designed targeted 0.0474 kilograms per second that we were aiming for. However, our manometer scale actually only went up to a pressure differential of 1.4 kilopascals, which of course is not the same pressure difference that we wanted to achieve, which is 1.6 kilopascals. Now, this is due to the manometer equipment itself not being able to actually reach the ranges of pressure that we were trying to test for. And this actually kind of leads us into our conclusion that the pressure differential did not reach the required 1.6 kilopascals that we wanted, which I mentioned before. This is mainly just due to a fault in the manometer and the testing equipment setup. It is also possible the tests could have been inclusive due to just larger error analysis. This is also just a fault due to the equipment itself. Um, Future work would uh, have us testing a larger scale of manometer with a larger inches of water difference that we can measure at. Also, more tests just in general, just to get a mass hysteresis error analysis and a general mass analysis that we can get. And additionally, the test setup itself was actually flawed in the fact that our jig that we attached to the blower motor itself, attaching to the restrictor, was actually most likely not long enough to achieve the fully developed flow to get a more conclusive pressure data from our restrictor taps. Additionally, more pressure taps along the restrictor, especially around the radius of the restrictor itself, would be required just to get a better uh, pressure scale across the restrictor itself, and then be able to average those numbers out at each point along the same circumference in the restrictor.